Okay, greetings to all of you. Welcome to the channel. I am Surendra. In the last part, we have solved some of the problems related to um electron injection into silicon substrate and finding number of free electrons, free charge carriers in germanium. So now let's solve some of the problems related to electron density charge profiles distribution during injection of charge carriers. So let's start with this question, sixth question. So they say that in example 2.9, compute the total number of electrons stored in the material from x equals to 0 to x equals to L. Assume the cross-section area of the bar is equals to A. Okay, so basically first we need to see what is there in example 2.9. In example 2.9, they say that in example 2.9, they say that the electron density follows this profile from x equals to 0 to x equals to L when injected into a substrate from one side. Okay, now note that this is not the formation of electrons when they are injected. This is the concentration profile. What is concentration? Concentration is number of electrons per cubic centimeter. That means if you take a slab of infinitesimally small block, you get some more number of electrons at x equals to 0, but when you go as along the length of the block you get very less. That means something, it will be like this: it is more spreaded as you go along the substrate, but it is more confined at the beginning of the substrate. So this is not that you need to calculate volume of the uh, this block, that means this rectangular block. Instead, we need to calculate volume of the whole block because the electrons are spreaded. Electron per cubic centimeter will be decreased as you go along the length. Okay. So how do we do this? They gave, okay, we can see that this means that n of x equals to, this is a straight line, right? We can write y equals to mx plus c. M will be negative, so it will be minus. Slope will be n by L x. Okay. uh, yeah, plus n, because at x equals to 0 it is n. Okay, this is electron density. Now if you take for small volume the number of electrons will be n of x into dv1. For small volume, the next slab, if you take dv2, it will be n of x into dv2. Like that, if you go on add n of n to the end of the block, you get n of x equals n of x into dvn. So to get whole number of electrons, you get integral n of x into dv, where dv is the summation of all the volumes. So dv is the area of this block times its length. So it's equals to integral n of x a dx. Okay, now a comes outside. N of x is minus n by L x plus n dx. Is from 0 to L. Now we can write a, this is minus n by L x square by 2, 0 to L, plus n x 0 to L. Okay, this is will be minus a n L by 2 plus a n L. So it will be a n L by 2. So this will be the total number of electrons stored in this material from x equals to 0 to x equals to L. Now let's see next problem. So the next problem says repeat the problem 6 for example 2.10, but for x equals to 0 to x equals to infinite. So we have that the concentration profile now is exponential. Okay, this is negligible, that means it touches 0. This is n, this is x. So n of x can be written as n times exponential of minus x by ld, where L is the length of diffusion, not length of the substrate. So similar concept, if you apply, total number of electrons equals to integral n of x times dx, a n of x times dx, but limits are 0 to infinite in this case. So a n exponential minus x by ld dx 0 to infinite a and n exponential of minus x by ld by minus 1 by ld 0 to infinite. E power minus infinite is 0, e power 0 is 1. There's already minus, so if you write 0 minus of minus a n ld, so it is a n ld. So if we compare these results with the previous one, for the exponential profile, the number of electrons depends upon the length of diffusion, but in linear profile, uh, total number of electrons depends upon the length of the substrate. Okay, now this is done. Let's move on to the next question. They say repeat problem 7. If the electron and hole profiles are sharp exponentials, they fall to negligible values at x equals to 2 micrometer and x equals to 0. Okay, now the limits are not 0 to infinite, it's 0 to 2 micrometer. Considering sharp exponentials, like electron and hole profiles are exponential. Okay, now we can write n of x as, that is n exponential of minus x by ld, correct? Now p of x will be, it is opposite to that and shifted to in its right side. So it will be exponential of positive x by ld. It will be minus 2 because it's shifted 2 times right side. Both are electrons, I mean electron per cubic centimeter. This will be holes per cubic centimeter. Same thing. If you apply total number of electrons for this, you will get A and LD. Okay. No, no, no. This is for 0 to infinite, right? Okay, we will do calculations. Let's take a new page. So, uh, yeah, n of x equals to n exponential of minus x by ld. P of x equals to p exponential of x minus 2 by ld. Electron per cubic centimeter, hole per cubic centimeter. Now number of electrons can be written as integral a n exponential of minus x by ld dx. It will be a n ld into exponential of minus x by ld. Limits will be 0 to 2 micrometer. Okay. Now expanding this, we get a n ld exponential of 2 micrometer by ld, and okay, minus e power 0 is 1. Now p is equals to integral a p exponential of x minus 2 by ld dx. A p exponential of x minus 2 by ld, this will be 1 by ld, and limits will be 0 to 2 micrometer. Okay, now apld, if you put values you get 0, that means 1 minus e power minus 2 by ld. Okay, if you compare these two, basically length of diffusion will be so small. That means there's a fact that length of diffusions are way less than, some amount of micrometers. Okay, that means that e raised to 2 e raised to some amount of number by a smaller number than micrometer makes it so larger. Okay, as it is negative, so e power some big number is 0, so we are left out with a n ld. Okay, so n equals to a n ld, and similarly E power minus 2 by LD will be 0. Same, P will be AP LD. So yeah, we see that the length of the diffusion is, sorry, the number of electron or hole concentrations are dependent on length of diffusion, but not length of the substrate. Okay. So yeah, this proves the previous results. Okay, this is good. And yeah, let's go to the next question. Let's go to ninth question. They said, let's see what is drift current in our electrical first. If there is an electric field flowing in this direction, if you put a positive charge, it flows along with the electric field. If you put a negative charge, it goes away from the electric field. So basically, there are some forces that acts upon charge carriers. Okay. Now let us consider a plate. It is aligned with the floor in your room. Okay. Let's say we have marbles in them, and you are holding this plate with your hands straight such that this is parallel to the floor. Now let's just tilt the plate one side above and one side below. If you do that, you are creating a change in, so basically all the marbles are pulled downwards. Okay. Now if the plate is tilt, then the force will be exerting like this. Okay. The net force can be resolved, but the actual force is pulling like this. Okay. So yeah, this means that some of the forces acts on the marble, makes the marble move. So this is something similar to our drift current. Okay. Yeah. Okay. All right. So we have solved some of the problems related to electron densities, right? In the upcoming videos, we'll solve some of the more problems. So make sure you're following the series. And yeah, thank you. Bye. We'll meet you in the next video. Bye.